Okay, so this is what, like, initially it may show some tendency, but we don't know after a particular period of time. That is what we call as dynamic stability. After a particular period of time, so at 30 second, the rocket is experiencing some disturbance. We are not worried about what happened immediately to the rocket, whether it is showing some tendency to come back or not. That is not a matter over here. But after a certain period of time, let us say 1 minute, 1.5 minutes, what is the position of the rocket now? Whether it has come back to its original position. That that is what we call as dynamic stability. So it is the tendency of the rocket to regain its original position after a certain period of time. Okay, so it is a tendency of any object to come back to its original position after or in a certain intervals of time after. Okay, this is what we call as dynamic stability. Guess what happened? You can hear me, right? Someone trying to say something? Okay, so this is what we call as dynamic stability. After a certain period of time, you are observing how the object is, whether it is regaining its original position. If it regains, fine, we can say it is dynamically stable. So basically, when we more particularly when we talk about aircraft or rocket, it has to be statically also stable. It has to be dynamically also stable, because there are few scenarios, few objects can be statically stable. So our design should be in such a way, it should not be only statically stable. Because let us say, this is a common practice even in aircraft also. Initially, it shows some tendency to regain its original position, but after some period of time, because of the adverse effect, whatever happened at this particular point, that will show some bad effects on the aircraft, and over a period of time it will lose its stability. Initially when you see it tries to come back, so we will say it is statically stable, because immediately when it gets some disturbance, it tries to come back to its original position. But over a period of time, when you observe, even though it tries to come back to its original position, it cannot stay in that position, and over a period of time the movement gets more worse and worse, and finally it loses its stability and all. So we can say this as a statically stable, but dynamically this object is not stable. So that is again not good for us. So our design criteria should be in such a way that the rocket is statically as well as dynamically stable. Now again, the statically stable, we are just we have three types of static stability. So okay. So one is positive static. Second is neutrally static. Third is negative static. What do you mean by this positive static, neutral static, negative static? We know static stability is nothing but initial tendency. Immediately after getting a disturbance, immediately how the rocket is responding or the object is responding to regain to its original position. Now, positive static in the sense, let us again consider the rocket. Let us say this is a rocket. Some point of time it got some disturbance. Okay, this is a rocket. It got some disturbance, and immediately it is trying to immediately it regains the original position. Okay, It was like this initially. Okay, this is the line of symmetry. Let us say this is the direction of its rocket. Initially, it was like this because of some atmospheric drag. It got slightly deviated in its path. It becomes like this. Let us say. Okay. Okay. But in a due time, it shows some tendency to regain it to its original position, and it came back again like this. Okay. So we can say this is positive static because immediately it shows the tendency to regain its shape, original position. Neutrally static is like it got deviated. Initially, it was traveling like this. Okay. Initially, the rocket traveled in this path. It slightly got deviated like this. Okay, a very small deviation, and immediately it is trying to come back. Okay, but it has not come to this position, but still it is maintaining a path. Okay, with the disturbance, with the disturbance, it is still maintaining a path. Okay. So in this case, like it is still remain in a new position, and it continues the path the mission gets succeeded. Let us consider like that. So that is what we call as, but still it takes a decision immediately and maintains this position further. But the mission continues. It is not a failure. Negative static in the sense it totally like immediately it tries to come back, but what happens is it cannot come back to the real position but takes a totally new position. Okay, it totally takes into a new position immediately, as I said, it moves like this. uh, but it shows some tendency to regain its original position, but what happened is it further moves in this way, different position it further moves, which is negative static. Why we are since again saying a static here is because it shows some tendency to come back, but it couldn't come back. But further it takes a new position, immediately it takes a new position, which means if it goes like this, of course the mission cannot be succeeded, the rocket fails, right? So this is always not good for us. Similarly, neutrally static is also not good for us to some extent. In the case of rocket or in the case of aircraft, even this cannot be encouraged. But to some extent, we can say neutrally static. It may be because today's rocket technology, we have a lot of other systems further to control, even though it maintains the path. But when it is negatively static, it tries to come back, but it couldn't come back. Totally, it is deviating the path. It somewhere it fails and drops in the sea, let us say. Okay. Now, similarly, negative stability. I mean, dynamic stability. So this positive static, we should maintain a design, or we should have a rocket in such a way it should be positive static. Okay. Now, dynamic stability. Okay, so dynamic stability, as I told you, it is a tendency to come back to its original position, or the tendency of the rocket to regain its position, or the tendency, or the yeah, we can say the tendency to regain its original position, not immediately. After a particular period of time, how it is reacting to the disturbance that happened before some period. Let us say that's what I said. An example of 30th second, there was some disturbance, but we are observing at a second minute because of the disturbance happened in the 30th second, how the rocket is responding in the second minute because of this disturbance, whether there is any disturbance in the second minute. So after a particular period of time, how it is responding, that is what we call as dynamic stability. And again, here we are describing it into it has three things. One is positive dynamic, neutrally dynamic, negative dynamic. Okay, so positive dynamic, let us say. So this is after a period of time. Immediately it won't happen. Okay, it takes some few cycles to analyze this. Immediately we are not analyzing. Whereas static stability is immediately, statically, immediately. When the disturbance happened, immediately how it is responding. So dynamic stability, we can't tell like that. It takes some time. So let us say, at this point, it got some disturbance. Okay, the amplitude is more, the disturbance is more, but over a period of time, slowly it is regained. Okay, initially this was the path of the rocket, let us say. Okay, the rocket was moving like this. Okay, it was moving like this, but at this point it got some disturbances. Immediately it is not regaining, but it got completely disturbed. It is moving like this here and there. Okay, okay, it is totally wobbling, and but at a certain, after a period of time, it is getting controlled. See, it is getting controlled, and after over a certain period of time, again it comes back to its original position, right? It has regained its original position again as how it was before. Okay, so this is what we call as positive static. Initially, like immediately you can't analyze what is happening, but over a period of time, it is good. It is making something good. It is maintaining again the same flight path. Okay, whereas neutrally dynamic, we can say again the rocket is traveling like this. Okay, I'm just making that's all. Now what happens is here you got a disturbance. Now what happens is this amplitude maintains in the same path like this over a period of time, which means it will not come back to this original position. It will continue the path with the disturbed mode, but it will not fail. You are getting it cannot further travel in the straight line, but at the same time it will not fail also. It will wobble with some disturbance. Somehow you are ending the path, but disturbance will be there. That wobbling will be there, or whatever it is. That because of that, let us say aerodynamic effect, something deviated. The deviation will be there over a period of time. That exists, but still the mission will not be failed. The rocket will not fall down. It won't loses the stability, but it takes a new it travels like this with some wobbling effect, with some adverse effect. It continues the path. Whereas negative dynamic, okay, initially traveled like this. So again, one more question you will be where we can analyze the static. Static is immediately at this point. Immediately when there is a disturbance at this point, immediately how it is responding within fractions of seconds. Okay, so this is over a period of time. This is a, let us say 30th second. So 31st second, let us say static, not even 31st second. Immediately how it is responding. But this will be some 50th second, this will be some 60th second, 70th second, like that over a period of time. Okay, but 30 to 31 second, that is we can say static. Immediately how it responds, but over a period of time, this let us say somehow it comes to 1.5 minutes. Okay, 80 seconds, not 80, right? 90 seconds. So at 90th second, how it is been responding. Whereas negative dynamic, again, we are analyzing over a period of time. At this point, some disturbance have happened. Okay, and what happens is immediately it moves like this. Okay, we are thinking that it is going in a neutral path, but over a period of time, after 1 minute, what happened is this could not come back to the original position. This is not positive dynamic. So what happens is, and at the same time, it could not maintain this path also further, but for rather than it is totally getting disturbed and it is increasing. Okay, the wobbling effect or the adverse effect is increasing, and finally somehow it takes a new path and it totally drops the rocket somewhere. It drops into the sea, let us say. Okay, because it couldn't maintain the path, it totally deviated and thrown out. Okay, because but when you analyze over this period, we can say it is trying to become neutral, or we can again say it may come back to positive static, but we don't know after a period of time. That's what we said. Immediately we can't, but when you analyze immediately, you will say this is stable. It is neutrally stable, but again over a period of time, it is not stable. It is totally getting out of box. That is what we are saying as dynamic, negative dynamic. Okay, and now like one more thing is there. Few one assumption we can consider is consider a rocket to be statically stable, but dynamically it is not stable. Again, I'm just considering the same scenario. A rocket is there. Okay. Okay. So it got disturbed at this point. Okay. But the tendency of the rocket is made it to come back to its original position immediately. So here some disturbance happened, but immediately it regained its original position. It is maintaining still the flight path. We are thinking that it is statically stable, but when we analyze over a particular period of time, it is traveling. But because of this disturbance, even though it came back to its original position immediately, over a period of time, again some disturbance is happening, and that become totally, let us say, negative dynamic. Okay, this is also possible. So we can say this as this rocket is statically stable because immediately it responds to the disturbance and regains the original position. But over a period of time, it could not withstand that path. It is deviating from the real path and getting into some other position. So it is statically stable, but at the same time, it is dynamically not stable. Okay, it is statically stable, dynamically not stable. This is also not good for us. So our design should be in such a position. The rocket should be statically also stable, dynamically also stable, which means over a period of time, whenever there is a disturbance happening to this rocket, immediately also it should regain its position. And over a period of time, when you analyze, there also there should not be any disturbance. The rocket should continue its path in the same attitude throughout its path. So now you can say statically also stable because immediately it respond. It let us say some wobbling effect happened. Immediately it respond to that and it regains the path. It becomes statically stable. Okay, statically stable. But now you are analyzing over a period of time. After some 2 minutes, you are seeing the rocket. Again, it has been in the same position. So you are saying it is dynamically also stable. This is what we need. This kind of what to say, this kind of design criteria is what our requirement. Okay, now again we'll go further to see how the stability of the rocket can be defined in a further way. Okay, so when you talk about rocket stability, we to maintain the rocket statically dynamic, statically stable and dynamically stable, two things, or like there are two important things in the rocket. One is center of mass and the other is center of pressure. Okay, one is center of mass and the other is center of pressure. These two, few people have messaged me that I have removed them. I think few people have messaged me that they are not able to join. Ask them to let them try once again to rejoin. If not, we will see later. Okay. So two things are important in a rocket. One is center of mass and the other is center of pressure. So what do you mean by the center of mass? So any rocket, let us let us consider this to be a rocket. Okay. Yeah, we'll consider this as a rocket. Actually, it will not be a triangle, it will be a ogival shape, right? Okay. Because only then aerodynamically it can be. Okay, so this rocket, whatever rocket it may be, it has 2 points. One is center of mass and the other is center of pressure. So what do you mean by the center of mass and what do you mean by the center of pressure? How this is affecting the stability of the rocket? That's what we are going to discuss and we'll wind the class for today. Okay. So with respect to the center of mass, okay, let us mention it as CM. So the center of mass is nothing but it is a point at which the distribution of the entire mass of the rocket is equal in all directions. Which means the rocket will have payload, the rocket will have its own structural mass, it will have its fuel mass, which is nothing but the propellant mass, it will have its nozzle mass. So all this, entire mass of the rocket, individual masses of the rocket, okay, that will act as at a certain point. That point we call as it is the concentration of the entire mass of the rocket, and that will be equal in all directions. Okay, that point is called center of mass. So you will have again a question: what is the difference between center of gravity also? So center of gravity with respect to the weight, here we are not considering the gravity, but only the masses. But when you talk about center of gravity, it is with respect to the weight, with respect to the gravitational force of the earth. So for a rocket within the atmosphere, if you see within the atmosphere, always the center of mass and center of gravity will be same, because within the earth atmosphere these 2 points will be same in most of the case. It will be same, but uh, uh, here we are considering center of mass. Center of mass is like only the masses we are considering. Kilogram, the weight in the sense kilogram, like into 9.81. So it will be in newtons or kilonewtons. Whereas mass is in kg. That payload in kg, the structure in kg, fuel in kg. The entire concentration of the mass will act as at a certain point, where this point the masses will be equal in. From this point the masses will be distributed equally in all directions. That will be balanced. The mass will be balanced with respect to this point. So what happens is, with respect to this point, this will be tilting. For example, like this rocket can rotate with respect to this point. Okay, keeping this as a reference point, the rocket can rotate like this. Okay, this will be the reference point for rotation. Okay, keeping this point, it can tilt or rotate with respect to the center of mass point. Now what is center of pressure? So again there will be one more point, that is nothing but the center of pressure point, which we can say where the entire pressure of the rocket acts. Okay, so whatever pressure is acting to the surface of the rocket, that will be concentrated into a particular point, and that point is called the center of pressure. And if you analyze the area like if you say this to be the rocket, this area and this area will be equal from the center of pressure point. The center of pressure point will be balanced with respect to the areas of the rocket. To my geometry, it is not seeing like that, but you can analyze. Okay, you can just imagine. Yes, my geometry says that here you have more area and here you have less area, but you just analyze. Okay, the real pressure point will be somewhere where that differentiates the pressure, that differentiates the area equally in both sides. Okay, from this point, this if you consider this as a reference point, the area forward to the point will be equal to the area after the point. Okay, now how this is going to affect the stability, that is our okay. Now you understood center of mass and center of uh, pressure. And one more terminology. After introducing that terminology, I will move further. That is called static margin. Okay. There is one more terminology called static margin. Static margin is nothing but the distance between the center of pressure and the center of mass. This is what we call a static margin. And to maintain the stability, to have a stable rocket, the static margin should be at least 2 times the diameter of the rocket. This has been this has been optimized with various experimentations, and scientists have found that a static margin, if it maintains 2 times the diameter of the rocket. For example, if some 2 centimeter is the diameter of the rocket, the static margin, which means the center of pressure and center of mass, should be minimum 4 centimeter difference. There should be 4 centimeter distance between the center of pressure and the center of mass. So you should design the rocket in such a way the center of mass and center of pressure is acting at a distance of 4 meter. Now, how you could design that? That is again the design criteria, design beautification. For example, we'll again come back. So I said there should be some difference between the center of mass and center of pressure, right? Uh, let us say, of course, like we are maintaining the center of mass over here. Let me say, okay, center of mass. So overall, center of mass is nothing but includes the mass of the fuel also. Over a period of time, the mass of the fuel reduces because it is burning continuously. Huge amount of fuel is continuously burning out, whereas the overall mass of the rocket will vary because it is the combined, it is the average, or it is the concentrated mass of individual masses again, including the structure, including the payload, including the fuel, etc. So when the rocket moves, of course, there will be variation. Initially, you might have calculated at some point, but when you travel, when the rocket launches, because of the continuous burning of the fuel, this point will come back, right? Okay. Initially, you maintain a static stability to be exactly as per the criteria, but it is coming back because the fuel is burning. Now, how you are compensating this? And I said CP is nothing but like CP that divides the area. Okay, CP that divides the area into two half exactly. So one thing is like you are losing the mass now. One thing is you are losing the mass. So how you can increase the mass in the flight? Imagine the rocket is moving, fuel is continuously burning. Can you do that? Can you increase the mass at any time? We can't do that because suppose at this point the CM was here, center of mass was here. Once after a particular period of time, it will slightly move forward and it comes here. Okay, because the fuel is losing. You are losing the weight of the fuel, whereas the center of the mass will vary accordingly. Now, to compensate this, what you are doing is you should maintain the CM in such a way that it should be as much as in the front as possible. Okay. The static margin, what I said is minimum is 2 times of the diameter. The more you make, there comes your design beautification. So how to make that? Okay. Now what happens is the maximum to the front, if you could move the center of gravity, I mean center of mass. Okay. The more you move forward, and the center of pressure, the more you move backward. It is a good design criteria. But how to achieve this? Can you move the center of mass to this much forward? It is not at all possible. Why not possible? Because we have the fuel tank over here and we have the payload over here. At least, like if you can, it is possible when if you could move the fuel everything here, it is possible. But again, the structure won't be there, right? You cannot maintain that. Only in the front area you cannot maintain all the payload and the fuels. Not at all possible, right? You have to maintain the fuel here only, because that is the you can understand the structural stability over there. So to this much of moving CM forward is not possible. So what you can do is, let us say CM is somewhere here only, but the center of pressure you can extend. Yeah.
Sir, you are directly telling us like that the center of mass and center of pressure should be coincide such a way that there should not be any instability.
No, it cannot coincide together. It should not coincide at all. There should be at least 2 times the diameter of the rocket. Distance should be there between the center of mass and the center of pressure.
Sir, if what happens, sir, if it collides?
Which one? Center of pressure and center of mass.
Yeah, I'm saying that if they come to coincide into one point.
It will not at any time it will not come closer together.
Means I'm asking a hypothetical question, sir. If it happens,
No,
is there
if
any?
it happens, totally the rocket will become unstable. It will not be a stable rocket.
Okay, so that's why we have to maintain minimum two diameters for
Yeah,
the.
yeah. That again, little more we will come. How it is making unstable also we will discuss.
Okay. So these two diameters of a rocket is a experimentally proven one, sir. Or is
Experimentally proven. With a lot of experimentations, we have proved that.
okay.
So center of pressure, like as I told you, this maintains exact half of the area. The forward front, if you see from the point of center of pressure, the area front to this point and the area back to this point will be equal. But in this case, which I have drawn, it is not equal. So how to maintain that? So of course, it is not here. Center of pressure is not here. Let us say somewhere over here. But I want to maintain that here. What should I do? That that's how they introduced the concept of fins attaching. Now this area will be also included to this area. So overall, if I see this area and this area will be equal. That's how I am maintaining the CP away. Now, as you ask, like why the CM and CP cannot be at a point, there are reasons. CM point, this is the point where the lift and drag acts through. Sorry, CP, not CM, CP. Center of pressure is the point where the lift and drag acts through. Okay, CM is the point where the weight and thrust of the rocket acts through the weight and thrust will always act through the center of mass. Okay, now let us again, I will try to give you some understanding. Now you understood this, what is center of pressure and center of mass. And of course, the lift and drag is acting through the center of pressure, as well as, what is that? Center of mass is the point where the weight and thrust acts through. Okay. Now I'm deleting this. I'm just redrawing the.
Sir,
Yeah,
sir, now we have aerodynamic center in the aerofoil, right, sir? Like now we have any like that, like the same we have any center related to the air rocket, sir?
I didn't get you.
Like in aerodynamics, we have aerodynamic center now, sir, in the aeroplane
In
performance.
the rocket, you are saying?
Yeah, in the rocket we have any type of like that we have any center, separate center for a rocket, such that rocket will be stable.
Yeah, it is. It is.
Okay.
But only thing is, rocket. You have to understand one more thing. That's why even I am not talking. We are not talking much about center of gravity. Also, it is
Okay.
meant not only to travel within the atmosphere.
Okay.
I'm coming to that point actually. Like if it is an aircraft,
Okay.
it can come like what to say, that is what you are calling maneuvering. There are some maneuvering methods by which you can automatically turn over the aircraft to its original position because everything is within the air.
Okay.
But here, within the atmosphere, there are certain things you can even if it changes the position also, automatically coming back is very limited. But
Okay.
instead of that, you have certain nozzles which has a movement and that can be controlled from the ground.
Okay.
uh, we call them as gimbal thrust, gimbaled thrust, like gimbaled thrust in the sense, we use a nozzle in such a way that the nozzle will be swirled from an one side to other end, that can be controlled from the ground. So if it wobbled, if the rocket has been wobbled, because once if it enters out of the atmosphere, we don't know how the effect, like, because there won't be any air, of course. So aerodynamically, making the rocket stable is not possible at all.
Okay.
But instead of that, we are using nozzles to control and bring back to its original position.
Okay.
Okay. So, but still, till it crosses the atmosphere, the everything that happens to be in aircraft that suits for rocket also. So, as you said, there will be aerodynamic center with like everything it can regains to its original position with respect to the lift and drag. But once if you enter, once
Into
if
that.
you go beyond the atmosphere,
Yes.
there won't be any lift and drag because lift force automatically happening is not possible because air is not there.
Yes, sir.
So even fins also cannot give you any responses because air is not there.
Yes. Yes, sir. True.
Okay, so the only option we have is to control with a nozzle, and that too manually. We need to shift the direction of the thrust, and we can maintain the expected path of the for the rocket.
Okay.
Okay, so let us say this is your CM, center of mass, and let us say this is your center of pressure, and let us consider that this rocket has a fin. I think my fins are not correct, but still just try to adjust. Okay. Okay, something like this. So let us consider. Okay, now what we know with respect to the center of pressure, it is matching, right? It is like the area here and the area above will be equal with respect to the center of pressure point. Now, as you said, imagine that a scenario where a rocket is having like somehow it become in such a way that the center of mass
Yes, sir.
has, let us say, center of pressure is in the front and center of mass in the back. If suppose a rocket happened to be like this, what will be the scenario? What really happens is it will be moving in this path. Let us say some disturbance has happened in this rocket, and this center of mass, as I said you, this is the with respect to the center of mass, the rocket rotates, right? So what
Yes, sir.
generally? Sorry.
Yes, sir. You continue, sir. I'm just agreeing with your statement. That's it.
Yeah. So with respect to the center of mass, it rotates. So what happens is the center of pressure is the point where your lift and drag forces acts. So what happens is with respect to this point, it starts rotating. Okay. And here center of pressure, when it moves like this, at this point, your lift force will be more. Okay. And here it starts rotating. With respect to this point, it starts rotating. The rocket starts rotating like this. And here thrust is also a factor over in the rocket. So at a particular point, what happens is it cannot regain its original position, whereas it further tries to rotate with respect to the CM point because the lift is producing more when it got inclined, and the lift, but drag still it continues to be like this to some extent. But at a particular point, it totally deviates. And finally, what happens is it tilts upside down because this thrust is also pushing for further. And this movement, this lift further rotates the rocket. And at a point of time, it will become like this.
Yes, sir. Same condition happened to SpaceX recently.
Yes. So this is why we always say center of mass should be above the center of pressure point. If that is the case, if you ask me, will it not tilt? It will tilt. If you ask me, will it not tilt? Of course, it will tilt. But at the same time, the center of, the lift force, whatever it is produced here. I'll show you some. Is it time for us, or I think if I get some 5 more minutes, I will finish
Yes,
this session.
sir, 5 minutes. Yeah.
Yeah, because the next faculty will be also starting the session, I think. But I will request that Praveen sir, I will tell him to give
Okay.
you some 5 minutes break again.
Okay.
Yes, sir. Actually, I have not taken the attendance also. I need to take the attendance. Okay, I couldn't make an inclined diagram with this. I'll just talk. Okay, so let us say this is the path of the rocket. Okay, what happened? This is the direction. This is the flight direction. And from the CP point, there will be drag. And now there is no lift at all because it is traveling in the straight line. There will be, what are the forces acting? There will be only drag and thrust will be acting. Now what happens is, like let us say it is inclined because of some disturbance. It had happened to be like this. Okay. But your flight path is this. Okay. This is the axis. This is how you need to maintain, but it become like this. Now what happens is from the CP point, I think, let us say this is your CP point and this is your CM point. Okay. So in the CP point, it produces some lift and this will be your drag. Okay. But it cannot tilt much because CP is very further. I mean, there you have a lot of distance between the CM and CP. Whereas in the CM point, the weight is also acting. Now, when it got tilted, the weight is also acting. If at least this much of distance, the 2 times of the diameter of the rocket distance is not there, what happens is automatically this will start rotating with respect to the CM point. But here it is not possible because CM and CP are more forward. There is a lot of gap between the CM and CP, whereas which will not allow the rocket to rotate with respect to this point. You can imagine that. Okay, so what happens is this lift and drag will automatically, that is what we call aerodynamically, it makes the rocket to be stable. Further, it will regain its original position and it will continue to travel in the steady path. Similarly, if it tilts in this side also. Okay, but if we couldn't maintain the CM to be forward of the CP, then of course with respect to that point the rocket starts tilting and it will of course fall in the sea. Okay, now to maintain this again there are a lot of considerations. fuel, where to fix the fuel. That is the design ability of any person who design a rocket. To maintain this, how to maintain, that is the design ability. He has to make the diameter, he has to choose the diameter, he has to choose the fin size, he has to choose the height, everything based upon this design criteria. Okay, so I think we'll further discuss all these things. Let us stop today. It's getting late now. Okay, so thank you guys. Thank you. We'll